Hello there, geometers. This is obviously a geometry video. It's chapter 6, section 2. And today we're going to be talking about parallelograms. But before we get there, I wanted to give you a diagram of sorts of the different types of quadrilaterals that we have. As you can see, we have basically three branches of types of quadrilaterals. And basically the three different types are distinguished, separated if you will, by the number of parallel sides they have. So kites have no pairs of parallel sides. Trapezoids have one pair of parallel sides, and there's two different types of those. And then we have parallelograms, and parallelograms have two pairs of parallel sides. And obviously today's lesson is going to focus on the parallelogram portion. We'll get to trapezoids and kites perhaps later on in the chapter or in the course, but for now we're going to focus on parallelograms. And all of these are in the family of parallelograms. We have rectangles, we have rhombuses and squares. Rectangles, of course, have four right angles, and all of the sides aren't necessarily the same. But in the case of a rhombus, all the four sides are the same, but they don't necessarily have right angles. So if you combine the two and have the right angles and the congruent sides, then you have your squares. But like I said, we're going to get into that a little bit later. But we are going to be talking about parallelograms. And right off the bat, we have four properties, or four theorems, so to speak. But all of the theorems, at least these first three theorems, all start with the same hypothesis. So instead of writing it out three different times, I just wrote out the hypothesis once, and then each of these is the conclusions that you have. So all of these three things are true when you're considering a parallelogram. So it says, if a quadrilateral is a parallelogram, then one, opposite sides are congruent. So here I have my diagram of my parallelogram. And if opposite sides are congruent, then that would mean that JM would be congruent to LK, and that JK would be congruent to LM. And then we have the second theorem, which states that opposite angles are congruent. So there we have that angle M is congruent to angle K, and that angle J is congruent to angle L. And then the third one is the one that states that consecutive angles are supplementary. And that one can be kind of tricky, but basically consecutive means angles that are right next to each other. So it would mean these two angles, but it could also mean these two angles, and these two angles, and those two angles. So any combination of two consecutive angles in the parallelogram are going to be supplementary. So I've written here all of the four possible scenarios. It means that the measurement of angle K and L will equal 180, or that the measurement of angle J and M equal 180. Also, you could have M and L equal to 180, or J and... Did I put J and L there? I should have put J and K. So this piece right here should say K. My bad. All right? So basically all the consecutive angles are supplementary, which means that their measures add up to 180. We also have this last theorem, the fourth theorem up here in the pinkish color, the salmon-looking color. It says, if this one had a different type of theorem, so I didn't put it in the same ones as the ones before. But it says that if a parallelogram has one right angle, then it has four right angles. And that should make sense here, because if this is 90, and they both have to add up to 180, then this has to be 90. And if this is 90 and they have to add up to 180, then this is 90. And if this is 90 and they have to add up to 180, then this is 90. And so that's kind of how you get 99, so they're all going to be, so basically we get that if a parallelogram has one right angle, then they're all going to be right angles. So now we have example one, and it says the symbol that we use for a parallelogram is this little guy right here. They don't always put it, but that's the symbol, that's what it means. So this is going to be read in parallelogram ABCD, which we have here. Suppose that the measurement of angle A is 55. So I'm going to fill in some of this information. And segment AB equals 2.5. And BC equals 1 foot. Find each measure. They want me to find DC. since DC is opposite AB, and we know that from the previous one that opposite sides are congruent, then DC must also equal 2.5 feet. All right, the measurement of angle B. Angle B is over here, and it's a consecutive angle. They're not opposite angles, so angle B is not equal to 55, but we know that A and B should add up to 180. So that means that it's going to equal 180 minus 55. So basically what I'm saying is that 55 plus the measurement of angle B should equal 180. So I'm going to subtract 55 from both sides. And that's why I put 180 minus 55. And if I do 180 minus 55, I'm going to get 125. So the measurement of angle B equals 125. And so we'll put the 125 right here in my diagram. And then the measurement of angle C. Now angle C is opposite angle A. And our previous theorem stated that opposite angles in a parallelogram are congruent. So the measurement of angle C must also equal 55. And that's how you do that. So now you can try do it yourself, number one. And then we will move on to our next theorems about parallelograms. This time we're referring to diagonals. And what I've done is I've given you a little diagram. Again, I'm putting two theorems together here. If a quadrilateral is a parallelogram, then two things happen, two additional things. We already had four things from before, but concerning the diagonals, two things happen. One, its diagonals bisect each other. So first I've drawn in the diagonal AC, and I've drawn in diagonal BD. And when you do that, they bisect each other. Now, no one is saying that the diagonals are equal, and we're not even saying that this is equal to this. Well, we're saying that they bisect each other, so they cut each other in half. So we know that AP is congruent to CP, and we know that BP is congruent to DP. Not necessarily congruent to each other, but these two are congruent, and then those two are congruent. Also, in number two, we know that each diagonal separates the parallelogram into two congruent triangles. So basically, if you have one, it's kind of hard to see, but if you have one diagonal at a time, if I go with diagonal BD, then that triangle is going to be ABD. So this triangle right here is congruent to CDB, which is this triangle here. And then if you use the other diagonal, the AC diagonal, then you have ABC, so this top triangle, congruent to CDA, which is this bottom triangle. So basically the diagonals separate the parallelogram into two congruent triangles. Alrighty, so now we're going to see what we can learn by that. So it says here, if parallelogram QRST, or if quadrilateral QRST is a parallelogram, find the value of the indicated variable. So to find x, we know that opposite sides of a parallelogram are congruent. So QT has to be equal to RS. So 5x has to equal 27. So we'll come over here, 5x equals 27. Divide by 5. And we're going to get 27 divided by 5, which I believe is 5.4. But I'm confirming that here. Yes, 5.4 for x. In the case of the y's, we can see that we have 2y minus 5 here and y plus 4. And since the diagonals bisect each other, we know that both sides of the diagonal should equal each other. So 2y minus 5 should equal y plus 4. And then we are going to combine our y's and move our constants over. And 2y minus y is going to be 1y. And then y minus y cancels, so 4 plus 9. So we're going to get y equals 9 for part B. And then we have to find part Z. So let's see, where is Z? So here we have 3Z. And so we have a triangle here, Q, T, and S. But we also know that if this is in fact a parallelogram, the whole point of it being a parallelogram is the fact that opposite sides are parallel. So you can do this a couple of ways. One option is to recognize that the 33-degree angle and the 3z degree angle are alternate interior angles. So 3z should equal 33, which means that z equals 11. But another option for you to do is, that's the easiest option in my opinion, but the other thing that you can think about is that they're supposed to be congruent triangles. So QTS is supposed to be congruent to QTS to SQR. So if that's the case, then these angles should be congruent because they're corresponding parts of congruent triangles. And either way that you look at it, 3z is going to equal 33, and when you solve for z, you're going to get 11. So just two different options for you to go with. I prefer the alternate interior angles, but you can do whatever suits your fancy. So here's do yourself number 2, and then we will move on. It says determine the coordinates of the intersection of the diagonals of parallelogram FGHJ with the following vertices. Now we don't actually have to graph this parallelogram. It doesn't actually tell us to graph it, but what we do have to understand is where the diagonals are. So when you name a parallelogram, you have to go in like a clockwise or counterclockwise direction. So in a circular direction. I can't go F, G, H, J. I have to go F, G, H, J. And so my diagonals are going to be JG and FH. Okay, now that's important because to find the coordinates of the intersection of the diagonals, we know that they're supposed to bisect each other. So what I'm trying to find is the midpoint of JG and the midpoint of FH, and they should be the same midpoint because they're supposed to bisect each other. So the reason why I'm drawing the diagram is so I can see which ordered pairs am I supposed to be using. So the first thing I want to do is find the midpoint of JG. So I'm going to take J, which is -3, -4. And I'm going to take G, which is 3, 5. And I'm going to find the midpoint. And the midpoint formula was take the sum of the x coordinates, so -3 plus 3, and divide by 2. And then take the sum of the y coordinates, -4 plus 5, and divide by 2. So -3 plus 3 is going to give you 0, and 0 divided by 2 is 0. And 5 minus 4 is 1, so I'm going to get 0, 1/2. That is the midpoint of JG. And then to confirm my answer, I'm going to also find the midpoint of FH and hope that it's going to be the same. So for that, I'm going to use F, which is -2, 4. And I'm going to use H, which is 2, -3. And again, we're going to find the midpoint by taking the sum of the x coordinates, which in this case is -2 plus 2 divided by 2, and then the sum of the y coordinates, 4 plus -3 divided by 2. And of course, -2 plus 2 is 0, and 0 divided by 2 is still 0. And 4 minus 3 is 1, and then divided by 2. So in both cases, you get the same midpoint. So therefore, the coordinates of the intersection of the diagonals is 0 and 1/2. And that's how you do example 3. So now you can do the same for do-it-yourself number 3. And then we're going to go to our last example, which is our proof. And then we can call this video done. So it says write a two-column proof. We are given the parallelogram ABDG. So here's ABDG. And we know that AF is congruent to CF. So AF is this segment here. AF is congruent to CF. Okay, so what we have in our diagram, not our diagram, our proof over here, statements and reasons, we start off by saying that ABCD Why did I say ABCD? ABDG. Alrighty. We know that ABDG is a parallelogram. And so in a parallelogram, we know that opposite angles are congruent. So we want to say it's angle BDG. So over here we're going to put angle BDG. So here's angle BDG. This angle right here is congruent to angle A. Notice how we don't have to call angle A angle BAG because there's only one angle there, so we can just call it angle A. But in the case of angle D, there's 3 different angles there, so we have to call it BDG to be specific. And that's because definition of parallelogram. Because we know it's a parallelogram, that was one of our theorems. Now, we don't have names for those theorems, so we can't really call it, the parallel, theorem or whatever. But basically, by definition, because it's a parallelogram, we know that opposite angles are congruent, and therefore we can write that statement. We also know from the given in step 2 that AF is congruent to CF. And again, I don't know what's going on with me. I put CP here. That should be CF. So we know from the given statement that AF is congruent to CF. There's not even a P in the diagram, so I don't know what's going on there. But these two are congruent. And we can't really mark those in the diagram because each side is composed of 2 other sides. So now we know that because those 2 sides are congruent, then by the isosceles triangle theorem, we know that angle A is congruent to angle C. So here we have, if these 2 sides are congruent, then they're forming an isosceles triangle with base angles congruent. So now, we want to further state that angle A is congruent to angle C by the isosceles triangle theorem, right there. And then we're almost done, because all we have to do now is prove, we were trying to prove our last step here, that angle BDG is congruent to angle C. So what we have is that BDG is congruent to angle A, and then in turn angle A is congruent to angle C. So that means that BDG must be congruent to angle C, and that is because of the transitive property. And just like that, you have proven what you were set out to prove. And so now we're going to let you do this do-it-yourself question. And once you have completed this example or this do-it-yourself question, then you will have completed your notes for this lesson. And I will see you in class. And thank you for watching.